Hello YouTube, this is Prashant. Welcome to my log of chemistry where I record my work on chemistry. I hope it is useful to students as much as possible. In this video, we are going to be looking at redox reactions, and this time though we are going to be looking at a mathematical based question. Of course, this also involves a self-indicator. Well, let's have a look at the question over here now. So the question basically goes off like this. What volume of 0.4 molar Na2S2O3 would be required to react with iodine liberated by adding excess of Ki to 50 ml of 0.2 molar copper sulfate over here? Okay, all right. So let us try to break the question down. So what they are telling us is we are going to be having some reaction involving iodine happening over here, wherein we are going to be having Ki reacting with copper sulfate. Now in this reaction, what is actually going to be happening is copper is present in +2 oxidation state here and iodine is in -1. Now in this reaction, effectively what is going to be happening is we're going to be having the I- effectively becoming I2, and the copper 2 plus actually ends up becoming cuprous ion over here usually. So when this ends up happening over here, you will also be having sometimes copper also getting precipitated, but that is not that particularly often. Now what is effectively going to be the net result over here? We are going to be having iodine produced over here. So when we do end up having iodine produced over here, that iodine which is produced, they are telling us, is then reacted with S2O3 2-. So when I say S2O3 2- here, what is meant by S2O3 2-? S2O3 2- has a very common name. It is called as thiosolution or thiosulfate in reality. The actual chemical name is thiosulfate. Spelling may not be perfect over there, but I'm not particularly keen on the spelling aspect over here. So it's going to be called as thiosolution. More specifically, it generally is going to be present in the form of sodium salt of that thiosulfate, which is called as sodium thiosulfate. Okay, now so what is going to be the net reaction which happens now? The I2 again becomes I- and it ends up becoming S4O6 2-. That is a thiosulfate and ends up becoming S4O6 2-, which is called tetrathionate ion. Alright, it is called as tetrathionate ion, and you're going to be having, well, of course, a redox reaction happening over here. So net thing which is going to be happening is I- is converted into I2 in the first reaction, and then I2 gets converted back into I- in the second reaction over here. Now I did say there's going to be a self-indicator part over here, so let me give that clarification first, then we'll go into the mathematics involved over here. So when we talk about the self-indicator part over here, what does that really mean? The self-indicator part actually is like this. When you're going to be having this particular reaction, the iodine plus thiosulfate being done in a particular redox titration type of thing, is it really going to be a self-indicator or is it not a self-indicator? What does self-indicator really mean? Self-indicator means there is an automatic color change which is happening without any external indicator added over there. In this case though, it is not a self-indicator. In one of the previous videos, I had talked about permanganate behaving as a self-indicator. Iodine though is not going to work like a self-indicator. Most of you guys will be familiar with how iodine is tested. Exactly, the starch test. So starch is actually used as the indicator in this particular case over here. When starch is present, the iodine, the I2 which is present, will be showing a blue-black color. How do you test it out? Well, when you're going to be having any potato which has been peeled, if you drop a small bit of iodine onto it, you'll end up having the entire potato starting to turn blue-black in color. Check it out. That is basically meaning that the iodine is going to be having a blue-black coloration when it is present in the presence of starch over there. So in this case here, when the I2 converts into I-, the blue-black color simply ends up disappearing off straight away. So in this case, the I2 is not really behaving as a self-indicator. It is actually going to be something which needs an indicator. What is the indicator? Starch. Okay, usually we'll be having a drop of starch solution added in, which will basically make the solution in this second part of the reaction blue-black in color in the beginning, as the I2 gets consumed, we will end up having I minus being produced and the blue black color goes away. Alright, okay. They are asking what volume of 0.4 molar Na2S2O3 is going to be required over here. Now, let us try to understand a little bit more about the N factor aspect over here. See, in this particular case here, copper 2 plus is going to become copper plus 1. And at the same time, you're going to be having the S2O3 2 minus also becoming S4O6 2 minus. They're asking us for what amount of this would be actually required in the process over here. So let's try to understand that particular reaction over here. You're going to be having in this reaction here 0.4 molar of Na2S2O3 is used over here, correct? The straightforward formula which we are going to be looking at is going to be involving equivalents of the copper sulfate. So equivalents of copper sulfate in the first reaction. Let's call this reaction number 1 and let me name this second one as reaction number 2. So the simple principle we are going to be using over here is equivalents of copper sulfate in equation number 1 should be equal to equivalents of I2 in equation number 1. Now, let us now look at the I2 change which is happening over here, or the iodine change which is happening here. Iodine is going from -1 to 0 in equation 1 and it is going from 0 to -1 back in equation 2. So effectively, the N factor of I2 is going to be the same in both equation 1 and in equation 2. In the sense, we are going to be having the same type of change happening here. So we can say N factor of I2 in equation 1 is going to be the same as the N factor of I2 in equation number 2. Which basically means the equivalents of I2 in equation 1 are the same as equivalents of I2 in equation number 2. Why is this going to be the same? Because N factor of iodine is going to be the same in both equations. So this is true because N factor, what is N factor here? You're going to be having N factor being the number of electrons involved in the particular change we are considering here per mole of I2. So when I'm going to be looking at the N factor of I2, which is going to be dependent on the number of electrons which is transferred. In both cases, 2 electrons are transferred for every mole of I2, both in equation 1 and in equation 2. Why so? Same change is happening. If same change happens, same N factor. So we're going to be having N factor being same in equation 1 and in equation number 2. Meaning from here now we can extrapolate. Equivalents of I2 in equation number 2 are going to be the same as equivalents of S2O3 2 minus in equation number 2. So effectively, what can we now conclude? We can conclude that equivalents of copper sulfate is going to be the same as equivalents of S2O3 2 minus. Now let's figure out what is going to be the N factor for copper sulfate and N factor for S2O3 2 minus in both equations over here. So if I'm considering the copper sulfate over here, look at what is happening to the copper sulfate. It is going from +2 to +1, meaning N factor for the copper sulfate is actually going to be equal to 1. Now let us consider for the S2O3 2 minus in this particular scenario here. What is happening for the S2O3 2 minus? S2O3 2 minus here, as you can see here, is actually going to become S4O6 2 minus. So when it is going to become S4O6 2 minus, what is the oxidation number for each of these over here? Let's try to find out. So oxygen has to be -2 in both cases. So if oxygen is -2 in both cases, let's try to see what is going to be the oxidation state for sulfur here. So -2 net charge for the overall S2O3 2 minus. So each sulfur is present in +2 over here. Nice. And in S4O6 2 minus, what is happening there? There's going to be 6 oxygens, so -12. But there is a net -2 charge, so -10. That 10 negatives, or rather the 10 positives which have to balance it out, have to be shared by 4 of the sulfur atoms over here. So it is going to be in +2.5. So per sulfur, the actual change in oxidation number which is happening in the second reaction is 0.5. In S2O3 2 minus, there are 2 sulfur atoms. So the N factor for this also is going to be 1 in this particular case over here. Alright. So let's now look at how to play this out over here. So equivalents of copper sulfate in equation 1 should be equal to equivalents of S2O32 minus in equation 2. So let's put this down over here. So equivalents of copper sulfate in equation 1 is equal to equivalents of S2O32 minus in equation number 2. N factor for both of these fellows is going to be 1, meaning we can now say volume into molarity into N factor for copper sulfate in equation number 1 should be equal to volume into molarity into N factor for S2O32 minus in equation number 2. Let's now put the math down. Let's see what we get. So we're going to be having 50 into 0.2 into 1 is going to be equal to some volume V which we have to calculate multiplied by 0.4 into 1. Fairly straightforward now. 1 and 1 gets cancelled, 0.2 and this will go away, this will become 2. So V works out as 50 by 2, which means it is 25 ml. So in this particular case here, the correct answer is not what has been marked over here, but the correct answer is option Bombay, which is going to be 25 ml in this particular case here. I'll see you guys in another video. Thank you very much, guys. Please do share and subscribe if you found this video useful, and do share it with people who will also find it useful. Bye-bye.